this, I wanted to go through the problem 95 from Project Euler. The problem is called Amicable Chains, and Project Euler is a website for solving mathematics puzzles. It has multiple problems, so I just found this one interesting. So let's go through this one. So the proper divisors of a number are all the divisors excluding the number itself. For example, the proper divisors of 28 are 1, 2, 4, 7 and 14 except the number itself. So the sum is 28 and they are calling it as a perfect number. Interestingly, the sum of the proper divisors of 220 is 284 and sum of proper divisors of 284 is 220. So there is a chain formation here, forming a chain of two numbers, and for this reason they are mentioning that these two numbers are forming an amicable pair. They're also noting down that there are even longer chains than this one. So for example, if you start with 12496, this number, and at each time you keep on updating the number with the sum of proper divisors of that number, you are going to eventually, after 5 tries, arrive at the same position that you started. So this is again a chain of numbers. So if you arrive at the same position where you started, the same cycle is going to get repeated after this interval of 5 length. So this chain returns to its starting point and it is called an amicable chain. So the question now here is to find the smallest member of the longest amicable chain with no element exceeding 1 million. So they are bounding the numbers up to 1 million, which is 10 raised to 6, and we need to find the largest the cycle or the chain with the most number of numbers in it, and any number in that cycle is below a million. So this is the question. Let's go through some of the observations that will be helpful for solving this. So let's say the main requirement is to know the proper divisors of any number between below 1 million. So let's denote the sum of proper divisors of any number x by PD sum of x. So we need to compute this array for all the numbers up to a million. Next one, so if you observe any chain, the PD sum for A will be B, then PD sum for B will be C, and PD sum for C will be A. So the sum of prime divisors for the last numbers is the first number itself. So this is the main criteria for iterating over the numbers one after the other, and we don't know where the numbers are going to converge. We don't know the exact cycle length, so we need to find the cycle with the largest length, and in that cycle you need to find the smallest member. So if you model this problem based on the edges from one number to the other, you can see that a cycle is formed each time moving the starting position from x to PD sum of x. So if we keep on updating our variable x, which is the starting point for finding a cycle, and each time we are moving to the prime divisors, the sum of prime divisors of that number of x with that value, updating x with that value, we are eventually going to traverse a path which consists of numbers from one number to the other. And with this information you can model this problem as a graph. So you can see that the numbers are bounded up to a million, hence there will be a million nodes in this graph, and each node has at most one outgoing edge. So each I for 10 raised to 6 nodes in the graph, the node I has an outgoing edge from I to PD sum of I. For now, let's assume that we have already computed this PD sum value, and later I will show how this is computed. Then we just need to find the largest cycle in this graph. So the problem now boils down to finding the largest cycle in this graph that we generated. Let me also revise it once more. So we have 10 to 6 nodes in this graph, and for each node we have an edge from I to PD sum of I. And once we find the largest cycle in this graph, we just need to print the smallest node which is present in that cycle, the smallest value in that cycle, as it is expected in this question. Okay, so if you have to point out some of the observations from this graph, what kind of graph we are generating, we can see that this is a cactus graph. So what it means is each node has at most one outgoing edge. As we can see, for any node I, there is edge from I to some node PD sum of I. So if PD sum of I exceeds a million, we are not going to add that edge. So that's why I'm saying here that each node has at most one outgoing edge. So let's also diagrammatically go through how this graph is going to look like. And another property is no common edge between two cycles. So any directed graph may contain a cycle, and inside that some of the edges may intersect with another cycle. But the property of this graph cactus is that the cycles will be disjoint. No common edges will be present, or no common nodes will be present, because at most one edge comes out from a node. That's why it can only be a part of one cycle, and the cycles are disjoint. So let's also go through some of the examples. So as you can see in this example, each node has at most one outgoing edge, and the incoming edge cannot be there, or it might be there depending on the condition. So as you can see here, outgoing edge is not present, here incoming edge is not present. And as you can see, this is the largest cycle, and there can be some chains which are going to connect to this cycle. So eventually a cycle will be present in this graph, and some branches which are going to flow in this cycle. The cycle can be a complete cycle without any branches. It can contain multiple or none of the branches, or even a single branch which converges to a cycle, or even the forest of nodes may not contain any cycle. So these are some of the examples of cactus graph. So let's now go through the solution for finding out the largest cycle in a cactus. So the solution is, first of all, we need to find out the PD sum array that we mentioned earlier. So for all the numbers below 1 million, we need to find the sum of prime divisors of that number and store it in an array, so that it is helpful while adding these edges. So let's see how that is implemented. So it is very similar to sieve of Eratosthenes algorithm, which runs in n-log n time complexity. So we have a million nodes, so initialized mx with a million. Then we have the PD sum array initialized all with 0. Then we start off with a divisor from 1 to mx, and for all of its multiples, so as you can see, this variable loops over all the multiples of the divisor. First it will go through divisor, then twice divisor, then thrice divisor, and so on up to mx. And it is going to add the, since divisor is divides multiple, so we need to add the sum, add its value to the PD sum of multiple, so that it is counted in the sum. And one more thing to notice is, since we are adding the number in itself, so we need to subtract it, so that it only consists of the divisors that they are asking, which is proper divisors, not including the number itself. So that's why we need to exclude it, remove from the sum. And the time complexity for this is mx log of mx. You can refer sieve algorithm for this, how it is derived. This was the first part. Next one, we construct the edges of our graph. So for all valid edges, for all valid nodes between 1 and mx, we just add an edge from I to PD sum of I, and let's say instead of constructing a adjacency list or anything, we just store the node in a array itself. So since any node has at most one outgoing edge, this value might be -1 or some value between 1 and mx, so that we can determine if the edge is present or not. So next of I denotes what is the next node to go to from the node I, and after that we just need to find the largest cycle in this graph and print the node with the smallest value in that cycle. So let's now go through the cycle finding algorithm. So first of all, we need to start with any node for finding a cycle and keep visiting until you visit an already visited node. So since we are having cycles in our graph, we need to store what all nodes we are visiting in a particular iteration, so that even if we come to a loop, we don't end up in an infinite iterations in our program. And after that we cut the unwanted part. So let's see what that denotes. So let's say our starting node is this one, the green one, and we keep on going to the next node, also keeping the track of visited nodes at the same time. This eventually it ends up in a cycle, and all the green ones are now visited and our iteration may end. In the end, we can see that this cycle is going to be present in our list of visited nodes. So let's say we started here, then here, we came here. As you can see, this was the last node that was visited by our iteration. And now if we want to consider this cycle to update our answer, we need to cut off this part. This does not get included in our answer, so we need to exclude then consider this remaining visited nodes in our cycle. So one more thing to notice here is that once we cut off the unwanted part, our cycle will be ready. And let's see what all observations are present. So the same cycle can be found out using different branches as starting points, and we can ignore them if already processed. So let's also take this as an example. So let's say instead of this node as a starting point, we started off here. Now we are eventually obviously going to end up in the same cycle. So we started here, next, and eventually we are going to stop our iteration. So all the red vertices are the nodes that we visited in this iteration, considering this starting point. And as you can see, the same cycle is considered even if the starting nodes are different. So even if you started here, we are eventually going to end up visiting the entire cycle that we want to consider. So this was the main observation. So you can start off anywhere. We just want to go through the cycle and cut off the unwanted part. So regarding the cutting of the unwanted part, what we need to do is we need to find out the node which was revisited in our iteration. So we started off here, then we went here. Eventually when this was the last node that was unvisited, and we moved to the next node from that outgoing node edge, we end up here, and this node was already present in our path. So we know the position of nodes that need to be excluded. So we just find out the position of visited nodes where this node is present and just delete the first those many number of nodes from that, so that the cycle will be remaining in our visited path. We'll go through the implementation details so it will be more clear. So this, I hope this is clear. The same cycle is processed with different starting points. Even if you started midway, even if you started here, the cycle will be considered, and there is no need to again go through the same cycle if you start here. So this chain, wherever you start in this chain, eventually you are going to end up processing the cycle. And let's say you started here, these all nodes will be unvisited, the cycle will be visited, but next time if you start here, you are going to end up here saying that this was already processed, so we can just stop the iteration there. So there are some multiple non-trivial observations for the implementation. We can go through that after this. And the same steps needs to be performed for all the disjoint cycle. So since this is a directed graph with multiple forests, not all of them are connected, so we need to go through all of them independently and update our answer accordingly. And the time complexity for this will be O of number of nodes plus number of edges, because eventually we are going to end up going through all the nodes and edges at most once. And this part may depend upon the implementation, depending on what all data structures and algorithms you use to store the visited nodes and the information that is required for finding out the path. Yeah, so that is it about the explanation. So let's go through the implementation now. So the main part was to find out that the graph is a cactus, and how do we find out the largest cycle in this cactus. So I've written the solution in C++. Let's go through the one. So mx is the number of nodes that are present in this graph. So we have a million nodes, so initialized with 10⁶. We have PT sum, which is sum of proper divisors of all numbers from 1 to mx. Next is denoting the next node that we go to from the current node I, and we have a visited to mark the nodes as visited during the traversal. This is the initialization for PT sum array that we went through earlier. Next, we have some sample test cases that were given in the problem. So it was mentioned that the PT sum of 28 is 28 and 228 is 284. So I've just used these tests for verifying our initialization for PT sum. So this was it. Next, we initialized all the next values as -1. So if we don't initialize it, by default it will be -1. We are going to only update it if the values are between 1 and mx. So this code is going to update our next function, which next array, which is going to denote what next to go to from the current node. Next, we have this variable which denotes the best answer that we found out. So first value in this denotes what is the length of the cycle, and the second denotes what is the minimum element in that cycle. So if we found out one cycle, we need to update the information in this variable. For that we are using this. Next, we have we are going to iterate over all the starting nodes from 1 to mx, and if that node is visited, we don't need to again go through its implementation or the iteration, so that we have a linear time complexity. Next, we need to store what all nodes are present in this path that we are visiting. We keep track of what is the current node that we are at, and in this while loop we are going to go through all the nodes one by one. First of all, we need to stop the iteration if invalid node is found out, which is -1 initialized here, the next array. Next, we only visit the node if it is not visited already. If it is visited, we can terminate the iteration. Next, if we are at a valid node visited, we add it to the path and then update the current pointer. So if the pointer is at -1, that means we have not found out any loop. Let me also show this example. So If this is the case, we are eventually going to end up at -1. So this node does not have any outgoing edge. So this is the condition for that, and we don't need to update the answer with anything for this. We also assure that the path is not empty. Then we find out the index of the repeatedly visited node. So if this was the example, we are going to repeatedly visit this node. So first time it is going to go from the right, and again when it comes from the bottom, it is going to revisit but not add to the path. The variable current will be pointing to this node. So we just find out what is the index of that. But it could be possible that it is an incomplete cycle if we already process that cycle and we are at a intermediate position. We just need to exclude that because we have already updated the answer for that. So that is this condition. Then we get the cycle by getting all the elements from the index idx, because all the elements from 0 to idx were not part of the cycle, they were part of this chain. So we just find out the position and take all the elements after that, so that we will end up with our cycle initialized in this vector. We also assure that the cycle is not empty, and then we also, for confirmation, what I've done is I have checked that the values that the cycle assures is checked after finding out the cycle, so that the solution is correct. So I just found out the last element in the cycle. Let's say, for example, this was the cycle that we found out, and last element in this case will be D, and the first will be A. So it is initialized here, and we can assure that the next element that goes, the next edge that goes from D will be A. So this is the assertion for that, and we update the answer by first of all making the cycle length maximum, and then if it is maximum, then the minimum element in that cycle will be updated, and eventually our minimum element of the longest cycle will be stored in best dot second value. Yeah, overall this was the implementation. We went through all the details and hope it was clear. If you have any doubts, just let me know in the comments, and for more videos like this, do like and share and subscribe.